Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on foundations of cyber physical systems. So, let us continue on our attempt of discretizing continuous plant models. So, we will just start from where we left off here. So, one small issue in this derivation that we have been doing. So, you see these were the limits of this integral, right, and so this negative sign is already accounted for here because the tk terms comes first. So, this one be here, and of course, we have multiplied everything with e to the power a t on both the sides, right. So, that would mean fine you had these limits of e to the power I mean the initial term was minus a t here. So, you have a minus here, and once you multiply both sides with e to the power e t, this becomes 1, and here of course, you have then the resulting expression here is e to the power a t minus t k, right, minus 1 because of this multiplying of both sides by e to the power a t. So, this is 1, and the other effect is well, we are writing minus a t k first. So, this subtraction here, this minus sign is off, and due to this multiplying on both sides, here we have t minus t k, right. So, this sign is also not there, and with this if we just continue to the next slide. So, you will have this. Now, let us understand how this e to the power h comes. We will just explain once again. So, if you recall from the last slide, you had e to the power a t minus t k here. Now, of course, your t becomes like we discussed already k plus 1 times h, and t k is k h. So, you have h remaining, that is why e to the power h, right. So, again we will follow up the correction here. So, this is your phi, which is e to the power a h, and this is your gamma b u k h by a u k h by a e to the power h minus 1, right. So, these are kind of standard derivations from the continuous to the discrete time, right. You can find in most of the popular books. For example, one reference is the book on digital controller implementations by Astrom, and you can find this done in a similar method in that book only. So, like we said that for a given system, if we want to carry forward this discretization, you can even approximate this E series with the first few terms and just evaluate what is phi and what is gamma and carry on from there. So, fine, with this if we just continue, the next thing we have already talked about is the notion of stability in discrete time. So, in this case your systems, you have to interpret the poles and the zeros in the z domain, and here you have to just check whether the poles are located inside, on or outside the unit circle, and accordingly you will infer whether the system is stable, marginally stable or unstable. So, now let us come to the issue of, well, we have successfully understood that given the system in the continuous domain with parameters a and b, how to transform it to phi and gamma, right, and b, and this gamma equal to, if you recall, from this slide. So, it was b u by a e to the power h minus 1 u at k h, of course. And based on that we can derive phi and gamma, and then you have this discrete time model here. And for this discrete time model, let us be the case that we want to design the controller. That means, we want to place the system poles in a suitable location on the z plane, so that we achieve this similar thing, y is tending towards r as t tends to infinity. And you want to design the k and f values, so that you have a controller like this. Again, I will just repeat, the sign depends on how you model the system. If you consider u equal to minus k x plus f r, that is fine, that is how it will be in the flow diagram, and you can just proceed accordingly. So, this does not really matter. So, the first thing we talked about controllability in our previous attempt of basic controller design in the continuous domain, right. So, just getting back to that, here also you will need to do the controllability check, but let us also understand what do we really mean by controllability. So, an LTI system will be considered controllable if for any initial state, let us say it is x 0, right, for the initial state, and there is a control input. So, you have the initial state as x 0. The question is whether you can design this sequence of controls, that is a control input u t, so that you can ensure that your system is eventually steering towards a final state x t that satisfies your requirement of the target trajectory. So, in a nutshell, we can say that it is controllable if for any initial state x naught, a control input u t can be designed such that inside this finite timeline t, the state of the system reaches the target final state x t, which is let us say is near about to some reference r. Okay. I mean, it is really controllable in that way. So, I mean, so the question is, why do you really want to do this test? You will like to do this test in order to justify whether I should really attempt the controller design problem or not, right. So, the way we arrive at this controllability matrix is something like this. So, you just unroll x k plus 1. So, for x k you have this difference equation, right. So, be it in the continuous domain or be it in the discrete domain, I mean, you can just try this in both cases. So, if you do it in the discrete domain, so that would mean just you just keep on applying this equation for different values of k, right. So, you have this relating x k plus 1 and x k, right. Now, you can just unroll x k, that means you can represent it in terms of x k minus 1, then x k minus 2, like that. So, for example, x k if you unroll, you have this expression, right, because this is nothing but so that would give you phi square x k minus 1 plus phi gamma u k minus 1 plus gamma this u k, the gamma u k, which is the last term here, right. And in this way, if you keep on unrolling and if you go all the way up to x naught and u naught, right, then you get this sequence, right. So, you have phi k plus 1 x naught plus phi k gamma u 0. In that way, you can finally have this thing as gamma u k, right. So, you have gamma u k, then phi gamma u k minus 1 and so on so forth, right. So, what you can do is, well, let us bring this x term on the right hand side. So, you have x k plus 1 minus phi to the power k plus 1 x naught equal to, now the rest of the expression that you have, you see you can just write it as a dot product of this vector which is comprising only the phi and gamma terms, right, because this is gone to this side. So, what remains is well, if you look from this side, so you have gamma u k, then you have phi gamma u k minus 1. Similarly, the previous term here would be phi square gamma u k minus 2. In this way, at the last you will have phi to the power k gamma u naught, right. So, this is the representation, and if you see what this really means, that well, if this matrix will have a full rank, that would mean that well, you can really design this system of this system of u's, right, from u0 to uk, and this really would make a set of possible solutions for xk plus 1, right. So, that is why we will say that this system has a solution if this matrix starting from phi to so gamma to phi k gamma, this has a full rank, and that is why this is called the controllability matrix. So, the idea is that well, if you can check controllability and you see that the matrix has full rank, then this UKs actually exist, and otherwise this system of equation becomes trivial, and it is futile to go about designing the control inputs in that case. So, fine, this is about controllability, which we talked about earlier, and just to kind of appraise you, there is also a dual characteristics which is known as observability, where the intuition is to check whether the input is rich enough to determine the state. So, just like controllability, the dual property is that well, I will consider the system to be observable if for any final input over a time interval. So, you have this final input y t over this time interval, you say that it is enough to reconstruct its unique initial state. So, suppose you know y t, the question is given this whether you can I mean if giving the final input, it is a good enough information from which you can really reconstruct its state. Now, if you can look at a similar sequence of equations for y k, so you can express y k in terms of x k, and similarly you can write x k, you can just write this expression of x k unrolled up to x naught, and u and this u naughts up to u k minus 1 like we discussed earlier, and similarly you can write that for y k minus 1 and up to y 0, right. And from this system of equations you can write this representation, right. So, you have this times x 0 equal to this matrix comprising the sequence of y zeros, right, and this will also have a unique solution if this matrix that you have uncovered here, right, and that has a full rank. So, this tells you that well, from the observability point is that well, if I know the final output, the question is whether it is possible that there exists an initial state from which the system eventually steers towards the final output. So, you can observe that kind of states to be really true, and with that it eventually comes to the final output. But anyway, for our control system design problem, let us go back to the context. We are talking about controllability check. So, what we need to do is well, for our problem we need to do the controllability check, and then we will do just a similar thing like earlier. We want to choose the closed loop poles at some locations, and we will apply the Ackermann's formula like we discussed earlier. But now note that what we are doing is we are doing it all for the discrete domain plant model, right. And then you apply the Ackermann's formula and you apply the feed forward gain formula, and well, you have the controller's design. Okay. So, it all remains the same, and all you are doing is you are doing it on the discretized plant model. So, you just get a controller for the discretized plant model. So, fine, with this we will end our treatment here, and we now move on to the second part, where we will consider situations like well, how when you are executing the controller there may be some imprecisions or uncertainties in the system in terms of timing, and how those things can disturb your design and whether your system design actually accounts for that. So, what we essentially mean is well, you have the controller for a discretized plant. So, your controller is now a software which is fine, but now the software is going to run as a task and in a real time processor. So, there may be delays in the scheduling, there may be delays due to other tasks. So, due to such delays, the controller may not be executing and providing control outputs exactly at points when you want them to be there, right. So, due to such delays, whether your system's design is not satisfying the desired control performance criteria is something you want to know about. And so, how do I analyze that? and how I can design a controller which will take care of such delays and it will work and meet its desired target objective in spite of such delays. So, that is precisely what we will be looking for in this part of the coverage. So, some of these materials have been taken from Professor Samarjit Chakraborty's course. Of course, we have adapted it for our purpose. So, let us first talk about this idea that well, why such delays should eventually come in a control loop. So, let us understand that how embedded controllers are really implemented. Some of this we have already seen from our previous coverage on real time scheduling of multiple tasks together. So, when you are implementing a control task, you are also going to have some associated tasks. So, let us say you have a sensor task that is going to read some sensor data and process them to extract some state information. So, there can also be some A to D conversion, there will also be some image processing tasks, maybe some estimation tasks, etc., right. Some filters which are implemented as softwares, all these tasks will be implemented and they will be running in the real time. Well, there also will be some controller tasks which implement the actual control law and which will compute the control input. And note that control tasks, not all controllers may be simple pole placement based controllers. They can be, let us say, a data driven controller, they can be an optimal controller. So, it is not that all the controllers are very simple and they do not take much time to execute. Some of the controllers may be quite intensive in terms of their computation, and that is why they may give delays to some other tasks, other control tasks. Okay. And also the control input has to be sent to the actuator, where and for this conversion from the control input to a real signal that the actuator circuit would understand, you may have specialized software, right. So, for that you will have separate tasks. So, let us so for example, when we talk about sensing tasks, A to D conversion is part of the hardware job, but the signal processing, filtering, estimation, these are typically the tasks which are performed on the raw sensor data, and well, again this is the hardware task. And for the actuator side, like I said, that you have computed a control input, but when it is going to reach the actual actuator, it may be some mechanical device, right, and that may need some conversion here from these control values to some suitable converted values which this mechanical devices input is going to understand, right. So, you will also have a separate software logic which will do all those stuff, and that is what we can abstract out here in our analysis as a actuator task. So, now consider this example. So, note one thing, that we are not talking about a real example here, right. So, we are just taking an abstraction. We are saying that well, a sensor task will do this functionality, and actuator task may have this kind of functionality, but of course, in real life these things will vary based on the application, right. So, all we are doing is we are abstracting things out, and we are trying to see that how their timings are going to impact the mathematical model of the controller here. So, let us take a scenario. We have, let us say, a task graph. We have multiple sensors, right, and they are providing inputs to multiple controllers here. So, let us say sensor 1 and sensor 2, they are corresponding to some sensing tasks, right, and those sensing tasks, once those are done, they lead to some control tasks. So, sensor 1 and sensing 2, they are processing must precede control task TC1, and once the control task is done, there will be a corresponding actuation task, and then the output flows to actuator. So, if you remember our discussions on scheduling, we talked about actuations and communication from the actuation signal, there will be related communication tasks, etc. also. So, coming here, let us say the sensor is actually sampling some common information for multiple controllers. So, from this you have sensing tasks also specific to controller 2, and then controller 2 will execute, and then the actuation task corresponding to controller 2 will also execute, and all these tasks must be executing on the let us say a shared processor which is an embedded platform here. So, you have all these tasks that need to execute, and all these dependence relations need to be satisfied. Now, so for doing all that, you need scheduling. So, there must be a scheduler on this embedded platform which will schedule all these tasks in a particular sequence without breaking their dependencies, right. So, let us say we consider this sample schedule. So, let us say well Tm1 and Tm2 must precede Tc1 and Tm1 and Tm2 can execute in any order. So, let us say this is the order we have chosen, followed by Tc1, and then let us say Tm2 and Tm3 is executing here, let us say now, okay. And then well, after Tc1 has executed, only then Ta1 can execute. So, let us say we put Ta1 here and then Tc2 here and Ta2 here, right. And of course, there is no particular ordering required between Tc1 and Tc2, but let us say this is our sequence, that Tc1 comes here, Tc2 comes here, Tm3 is here, and like that. And let us say that well, this is the schedule that keeps on repeating, okay. So, this is the schedule that keeps on repeating, hey, this up to this, and then again as you can see this is just repeating. So, on the embedded processor, what you have is you have this task sequence. So, let us say this is a pure static scheduling. That means, you have this task sequence and they are just executing in this kind of a particular order, right. So, let us say the measurement or sensing tasks you have, their corresponding code is sensor 1 reading something from a port, then doing some processing, then sensor 2 reading from a port and doing some processing. This control task will execute the corresponding control algorithm, then there is the sensing task for 3, the third sensor, then some actuation work, that is sending some values to some specific port, and before that doing some processing, something like that. And then you have this control task and the other actuation task, etc. So, let us say this is the task sequence that is going to execute, and let us say you have one executing after another, and this is your timing diagram of these tasks, okay. Now, if you look at these different timing values, we have something marked as tau 1. So, tau 1 is what we call as the sensor to actuation delay of tau 1. So, once some value is sensed, the corresponding actuation value is computed and it is ready for the actuator after this interval. So, that is the sensor to actuator delay. Similarly, tau 2 is the sensor to actuator delay of the control task 2, and here you let us say you have the period of some control task. So, you have this as the period for task 2, and similarly you have this for the period of task 1, okay. So, here you have the period of task 1, that means after this inside another amount of H1, task 1 must repeat like that. So, when you are doing your mathematical modeling and design of controllers, we make one important assumption. So, what we assume is that well, these delays are very small or negligible, and we almost set them to 0. That means, we assume that well, once the measurement x is available, immediately I mean u equal to minus k x, that evaluation is instantaneous, because that is why we are writing the equation as u k. If you recall, we are writing it like this, right. So, here also the kth instant and there also the kth instant, and so we are assuming that this thing is happening instantaneously, but of course, that is not the case, as we can see that well, in real life you have these delays due to interferences from other tasks and actual execution time, mapping time, and all this stuff which will happen in a task in a processor. So, in general, this measurement or sensing tasks and the actuation tasks, they consume negligible computation time and they are kind of time triggered. That means, the sensor is always going to sense values and the corresponding processing tasks of the measurement will always happen in a fixed periodic manner. So, they are like time triggered, they are triggered by this period. Similar thing for actuation, the sensor and the actuation tasks are all kind of time triggered. So, this is going to work here, and then again exactly after this period h, this will again be triggered, this will again be triggered, something like that. So, like this actuation task is here, and then again after some this fixed period will repeat, and like that. Okay. Now, this TC, this control task needs finite computation, and typically the way it will be implemented is you will have a preemptive scheduler which can actually preempt this task in between its execution, provided there is something of higher priority to execute. So, that is why this is preemptive in many practical cases, and also we say this is event triggered, because this may have dependencies on processing, right, previous stage processing. So, only when those things are happened that may, and other high priority tasks do not exist, are not executing, then only this will execute. So, this is kind of decided based on the relative events that are there around it, right. So, it should happen sometime between Tm and Ta, but that exact time is not deterministic. It will be depending on the events that are happening around it, the other tasks and stuff. So, that's kind of an issue, and we need to understand that, well, does it affect the control design? So, let us say your task, the sensing task is here in blue, sorry, in green, and your actuation task is here, and after this fixed sampling period the sensing task is again time triggered, and in between you wanted to execute this control task. So, you started it some, I mean initially it was blocked by some other task, then it has started here, and then again some other task came and trigger some preempted it, again it started here, and it could not start initially because it can only start after the measurement of the sensor task executing, and let us say again it has to wait here because some resource, this resource is busy, and let us say eventually it executes and finishes here. So, and it finishes here, and let us say immediately here this actuation task could not start here, and so there was some wait because somebody else was occupying the CPU, and then eventually this control input was processed by this actuation task here, and this is where the actuation output is available. Sorry, this wait is also not due to preemption, but the reason is, please let me repeat this. So, like I said that typically the way we are designing is this sensing on the measurement tasks and the actuation tasks are going to be time triggered, because they are computationally lightweight and no need to make them as a function of some scheduling decision. So, they are going to be always happening with this regular interval h, not only for the sensor, but also for the actuation. So, your design should be such that this would always be kind of triggered from here actually. Up to this, the two start points, they will be separated by this h. So, that is why if you come to our next picture, you have a specific point, right, where this will work out and then this will start, and also exactly a point where TA is going to execute. So, and this point is decided based on the maximum response time you may be budgeting for the control tasks. So, let us say the control task, I mean by your design it will finish by that maximum response time, right. And after it got executed, before it got executed, let us say this is the ith instance, the sensor task or the corresponding measurement task must execute, and it will satisfy this precedence relation, and then maybe some other task of higher priority was executing, then it executed, then again it is preempted, then again executed, then again preempted, and it got finished here. Okay. But this guy, it can start because it is event trigger, it will start precisely here only, and that is why we have this wait. In between other tasks may execute and they may be preempted, again other tasks may execute, stuff like that, but the wait is specifically for this control loop, and so the data that has been computed by this control loops control task is still not being processed for actuation, and that is going to happen here. Okay. So, the way we are deciding this triggering point is that we are setting a deadline for this control task, and we are saying that, well, you must finish by this deadline, and that is exactly the time when I am going to trigger the actuation task. So, if you see, it is like that everything is happening in a cyclic fashion. So, Tm is time triggered with period h, Ta is time triggered with period h, but the relative offset between Tm and Ta, this is given as the deadline of the control task, and it must finish somewhere in between. So, like I said that everything is periodic, at least Tm and Ta and Tc, but among them this guy is time triggered, this guy is time triggered, they may have this mutual offset, and this offset time is the deadline inside which the controller must be able to execute. So, I hope this is clear. So, we are just showing that picture here in the time continuum. So, the way we are modeling is what we call as the constant delay model. So, like I said that Tc can finish inside various times, right. So, it can in various instances of Tc can have various finishing times. So, what we do is we can compute the worst case response time, and based on that we can fix a deadline for that. So, that it is greater than the worst case response time, and that can be my choice of offset for this task Ta. So, this offset will be equal to the deadline for the control task, and at different instances of the control task it can finish at various points, but all of those points should be inside the deadline, right. So, to sum it up, Tm is periodically triggered and period is equal to sampling period. Let us say the offset is 0, the Tm, the sensing is precisely happening right at the starting of the sampling period. Execution time is assumed negligible, okay, and the period is h. The timing model for Ta is, this is also periodically triggered, but like I said the offset is equal to the control task's deadline, because we want the control task's response to happen inside this deadline. So, this response time in the worst case should be less than this dc, okay, and sometimes it may be finishing here, sometimes it may be finishing here, but always inside this dc, okay. So, if you can see that this is the period here, and this is also precisely equal to h, and this difference is the deadline dc, and Rc, I mean this is basically dc here, and it can have several possible response times. Let us say for Tc1 the response time was R1, for Tc2 the response time was R2, Tc3 this is the third instance, response time was found to be R3. So, the worst case response time must be greater than all of these Ris, and it should be less than this value of deadline of the control task that we are assuming in this design, and that is equal to the offset of this task Ta. So, with this we have to proceed. So, what we are doing is we are assuming the constant delay, because we are getting a guarantee that Tc must finish before the delay. So, that when we model the system we will assume that well the control task may finish earlier, but it will not be that output will not be used the moment it is finished, because you see then the design will not be deterministic. I mean sometimes the actuation will be earlier, sometimes the actuation will be later on, and that may be very difficult to model. So, in a simplistic manner we assume this constant delay and we will implement it in this way. That means, even if it finishes early, the actuation happens exactly after the deadline. Now, why we will do it is because then the modeling of the system becomes simplistic, and then your parameters that you can derive for the system will be quite deterministic. So, let us say how this modeling can be done. So, the way typically we consider the scheduling of the system is that well the deadline is mostly considered as firm, that means the control task must finish inside this. Now, one important question is well what happens if the control task somehow overruns this deadline? Am I going to allow it to execute it, complete it, and then apply? So, that means do I allow for what we call as delayed control execution, or do we skip that execution? So, based on this, I mean how we implement the control, we have different kinds of models of embedded control tasks. So, in case we skip the execution, then that means this firm deadline thing is anyway not happening, and you are not updating the control for certain control task instances. Now, this gives rise to a concept called weakly hard deadline. Now, this is a popular way of implementing real time controllers nowadays. So, what people do is people show that well, for the control loop, as long as out of every k consecutive actuations you can actually achieve the actuation in m of the instances, you can theoretically prove that well this control loop is fine. Okay. So, in theoretical way I can show that well, as long as the controller actually updates for m out of k number of instances, the value of m and k is specific to the model and controller we are talking about. So, if this can be shown, and it can be shown in practice for many systems, then we have this idea of weekly hard scheduling. That means, well, my deadline is firm, but it is okay to violate the deadline in a bounded manner. That means, as long as out of every, let us say 10 consecutive deadlines, I meet 5 of them or 8 of them, I say it is fine, and that guarantee may come from the controller itself. Okay. So, that is called weekly hard. But anyway, this is for your future reference. Let us come back to our simplistic case where we are talking about firm deadlines. So, we will think that well, if a deadline mishappens, the controller is skipping, I mean the controller, I mean it is an issue for the controller. So, we are assuming that the design is such that the deadline is not missed, but what is happening is that controller always finishes its task inside the deadline, and then it waits, and once we have this time DC gone, the actuation task will be triggered exactly at that point, and the control update will happen. Okay. So, just to repeat, these are interesting task models, allowing the control task to execute. That means, you are allowing more time to compute UK, or you are not actually computing UK at all. So, here what is happening is UK is not updated. So, it just remains as UK equal to UK minus 1. So, these are the two situations, and accordingly the control loops behavior will keep on changing. So, the ideal discrete time case is this, that you start with the continuous time model, you have zero order hold sampling, your deadline is 0, that means immediately you get the control computed. So, you have this situation which we do not have here, and then you design the controller based on the discrete time model. So, from this you get to design this, and from phi, gamma and stuff you apply, and all this, on this you apply the pole placement or other techniques, and you derive k and f, and you have you see that well you are able to meet your objectives of catching up to the reference trajectory or not, stuff like that. Okay. So, that is your ideal discrete time case. But in this case your situation is different. You have to think that well, how should I design my controller that well I am able to tolerate this delay and nothing gets violated. So, fine, we will continue from here in the next lecture. So, I think our time is up here. Thank you for your attention.